welcome 4 of Engineering Maths 5. It's Eigenvalues and Eigenvectors. Hopefully you can see there's been a little bit of a technological breakthrough, hopefully. We'll see how it goes. I'm using a new kind of graphics drawing tablet thing, which means I actually can't see my own writing. So my writing might be slightly worse, but hopefully it'll be a lot easier to see on this than it was on a pen and paper. If you prefer the pen and paper, let me know and I can go back to that. It doesn't bother me either way. Right, so eigenvalues and eigenvectors can be used to decouple three-phase electrical systems. So that's where it would be useful in electrical engineering through symmetrical component transform. Now all that means is that we're using something called linear algebra. Now if you go on and study more maths in university, you'll learn far more about linear algebra and how useful it is to solving problems in loads of different scenarios. Now all this eigenvalues and eigenvectors unit is to give you a flavour of linear algebra, so that you know the basics of it and you can apply it a little bit, and so that you feel quite comfortable with it when you move on to university. Right, so the eigenvalue problems have the form A, which is a matrix A, times vector x equals lambda times matrix x. Now, A is a square matrix, x is a vector, or the eigenvectors of A, and lambda are the eigenvalues of A. Now remember I, this thing here, is the identity matrix. So if it's a 3 by 3, it's this matrix here. If it's a 2 by 2, it's that matrix there. So this is our kind of standard form that we're going to be looking at. This A equals lambda I x equals 0, because something being equal to 0 is really useful. Right, now the eigenvalue formula is far more useful to us, and what that tells us is if we have A equals lambda I, which is what we had above, but instead of multiplying it by x, we take the determinant of it, that should also be equal to 0. So this is our key formula for us solving for eigenvalues. So all we do is we subtract lambda from the leading diagonal. We then find the determinant of the matrix, and then we solve by factorising as it is equal to 0. Right, because that's what we always do. If something's equal to 0, we factorise. Now, you could end up with a cubic, which means you could, in theory, have to do synthetic division. The majority of examples in this have a common factor of lambda, so there's no synthetic division needed. Right, now that's all just seems like a lot of nonsense, but let me do a couple of examples to see what we mean. Right, so the key thing is that you've got your matrix A, you subtract lambda from the diagonal, you then find the determinant of that matrix. If it's a 2 by 2 matrix, it's quite easy. If it's a 3 by 3 matrix, it's a wee bit more tricky, and then you solve by factorising. Okay, example number 1. Find the eigenvalues of matrix A, which is 3, -2, 4, -3. Okay. Now, first thing we do is we're going to write down our formula, and that is the determinant A equals lambda times I is equal to 0. Now, if you remember from matrices, determinant means what happens is we can swap the determinant for 2 absolute value straight line type things on either side. Right, and what I said we do is we take lambda away from each thing on our diagonal. So that's going to be 3 take away lambda, and that's going to be -3 take away lambda. And that again is equal to 0. Right. Now, remembering from matrices, this absolute value or determinant sign, when it's on a matrix, means we do AD take away BC, right? So we're doing 3 take away lambda multiplied by negative 3 take away lambda, subtract 4 times negative 2. We're saying that's equal to 0. A times D take away B times C, or I've done C times B, it's the same thing. Right, so you multiply out your brackets. So that gives me negative 9 take away 3 lambda plus 3 lambda plus lambda squared plus 8 is equal to 0. So I've just multiplied out my brackets. So 3 times negative 3 is negative 9, 3 times negative lambda is negative 3 lambda, and just continued with the rest of that there. Right now, so I'm left with lambda squared, so I'll always write my lambda squared first, right? My 3 lambda, they cancel out, and then 8 take away 9 is negative 1. So I'm left with negative, with lambda squared, take away 1. And then what I said we do, when we end up with something like this, we then factorise. That means C, D, D. Okay, so is there a common factor in these two terms? No, there's not. But that is a difference of 2 squares. Because remember, that's lambda squared and that's 1 squared. So remember, difference of 2 squares means we set up 2 brackets like that. And it becomes lambda plus 1, lambda take away 1 is equal to 0. So it's a difference of 2 squares that I use for my factorising. Right, so same thing as always. Normally we've got x's, but instead we've got lambdas. So that means that either lambda plus 1 equals 0, or lambda take away 1 equals 0. So you move that across. So that means that lambda is equal to negative 1 and lambda equals 1. And those two things there, your two values of lambda, those are your eigenvalues. Simple as that. Don't think that's too difficult. Right. Example 2. So let's say that B equals 2, 7, negative 1, 6. Right, so it's the depth of B take away lambda I equals 0. That's my eigenvalue equation every time. If I want to find eigenvalues, which of course are lambdas, that's my equation every time. Right, so remember determinant swaps for straight lines in that side of my matrix, and you take away lambda from these two values A and D of my matrix. That's going to be 2, take away lambda. That's equal to 0. Okay, then we do AD take away B times C. So AD, because there's 2 terms in each of those things, I need to put them in brackets. So that's A times B take away B times C is equal to 0. Try and keep your equal signs in a line. I've not managed to do that, but if you were doing it, try and do that. Come on. Right, so we're then going to multiply out our brackets as normal. So 2 times 6 is 12. 2 times negative lambda is negative 2 lambda. Negative lambda times 6 is negative 6 lambda. Plus lambda squared plus 7 is equal to 0. So that just gives me lambda squared, 8 lambda oh, no, I've done the question, I missed that a negative sign. I've done that in the question. Oh, that's what I've done. The question's done a negative in there. Right, mistake. So let's go back and change this. Right, so I've got take away lambda, negative 6 take away lambda, take away 7 times negative 1. So that gives me negative 12, take away 2 lambda, plus 6 lambda, plus lambda squared, take away 7, sorry, plus 7 is equal to 0. So that gives me lambda squared plus 4 lambda take away 5 is equal to 0. So sorry about that, that was my mistake, it should have been a negative 6 in there. The reason I didn't continue with the one with 6 is it wasn't going to factorise for me, so it wasn't going to be nice. It was going to end up me having to use quadratic formula or something. That's not something we want to do with these eigenvalue questions unless we can really avoid it. Right, so C dt. Right, so there's no common factor. It's not a difference of two squares. It's a trinomial. So adding and multiplying. So as usual, adding to make 4, multiplying to make negative 5. So 1 plus 1. 1 must be positive, 1 must be negative in order to make a negative through multiplying. So 1 plus 1 minus, and the only way making 5 is 1 times 5. So that must be negative 1 and plus 5. Okay, so lambda take away 1, lambda plus 5 is equal to 0. So lambda take away 1 equals 0, lambda plus 5 equals 0. You just move your negative 1 across, so it becomes 1. And you move your 5 across, so it becomes negative 5. And those are your two eigenvalues. Right, now I want you guys to try the following questions. Find eigenvalues. Right, so A is matrix, and hopefully I won't make a mistake this time. 1, 1, negative 2, 4. B is 13, negative 4, negative 4, 7. And C is our matrix 3, 7, 0, negative 4. I'll change that, looks like a 3. It's a 7. Right, and that's a 7. Honestly, it's not as easy using this little writing thing as you would think. Right, so those are your three matrices. Can you please find the eigenvalues of them by pausing the video now and trying on a bit of paper. Okay, so for this one here, you should have got lambda equals 2 and lambda equals 3 for A. For B, we should have got lambda equals 5 and lambda equals 15. And in C, you should have got lambda equals 3 in lambda equals negative 4, sorry, negative 4. Now, if you notice, this matrix here is called upper triangular. So can you notice that if you've got a 0 down there, it's that upper triangular matrix from Gaussian elimination. So in that case, the eigenvalues are just the diagonal of the matrix. But can you see in all of those, if you add the diagonal together, it's the same as adding your eigenvalues together. You add the diagonal, it's the same as adding your eigenvalues together. So after you've done an eigenvalue question, you can always check your answers by just checking, by adding up your diagonal and seeing if you get the exact same thing. Right, so that's finding eigenvalues. Really straightforward, it just turns out it's you take away lambda and then you factorise. Simple as that. Right, now, we now need to go on and look at eigenvectors. So this is the eigenvector problem. Okay, so this is the eigenvector problem as we saw in the last slide. Right, now, to do this, it's a few steps, 4-step process. 1, you calculate the eigenvalues just like we did. So we use the determinant of a take away lambda I is equal to 0. Then you substitute each eigenvalue back into the equation above. You then use Gaussian elimination, which I just spoke about, to make it upper triangular, as I just said. And then step 4 is we solve to find each eigenvector. Right, so let's have a wee look. Right, I just want to go through a couple of things just now rather than doing it in a question, right? So you might end up with, when you've done Gaussian elimination, 5x1 plus 2x2 equals 0. Right, what you do is you move it over to the other side, either one. So it'll be negative 2x2. Right, now, what that means for your eigenvector is, right, it's the opposite of what you think. So your eigenvector for this one right, so x2 is going to be 5 and x1 is negative 2, right? So t is what we write next to every eigenvector, just to say that eigenvector can be multiplied by any number t. So x1 is negative 2 and x2 is 5. So it's just the coefficient of the other element once you've got down to that problem. Right, if you had 9x1 take away 18x2 is equal to 0, that should be a t. Right, what we do is we same thing again. So 9x1 is equal to 18x2. Now, what you've then got to do here is see if they simplify. 9 and 18 are both in the 9 times table, so that would be 1x1 equals 2x2. Let's take away there. So that means your eigenvector is t, because we always put that in for eigenvectors just to show these eigenvectors is a general vector. And so x1 is going to be 2, so that goes in the top, and x2 is going to be 1, so that goes in the bottom. So that's how you do the second bit of the eigenvector problem. But let's put the whole thing together in a proper example. Okay, so after you've done Gaussian elimination, you'll be ended up with some kind of equation that looks like this. Why does that take place to keep going away? I don't know. and then simplify our vectors if we can. Right, okay, example number 1. And I've copied this over from our previous year's stuff. It's to make things hopefully a little bit clear. I know maybe my writing's not clearer, but I think sometimes the paper and pen was maybe a wee bit difficult to follow, but as I said, let me know. Right, so find the eigenvalues and eigenvectors of the matrix A, which is 2, 7, -1, -6. As I said, these are all going to work out with nice answers. Right, so first thing, we're going to work out our eigenvalues. Right, so our eigenvalues is the determinant A take away lambda I is equal to 0. So that means determinant means our square brackets, and so that's going to be 2 take away lambda and 7, and then -1, -6 take away lambda is equal to 0. Okay, so then we do AD take away BC. So that's 2 take away lambda, -6 take away lambda, subtract 7 take away -1. Sorry, 7 multiplied by -1 is equal to 0. Right, multiply out our brackets, and to be fair, I think this is the example we've already done, but let's just go through it anyway. In fact, it's the exact same example. So that means that lambda squared plus 4 lambda take away 5 is equal to 0. So again, that's when we choose to do CDT. We run through as usual. There's no common factor. There's no common factor there. There's not a difference of 2 squares, so it must be a trinomial because there's 3 terms. So that means I'm adding to make my plus 4, and I'm multiplying to make my -5. Right, so again, positive, negative, 1, 5 is the only way I can do it, so that's -1 and positive 5. I need to keep this equal to 0 all the way down. So as before, I'm just going to shorten it this time. Lambda is equal to 1. Lambda is equal to -5. So those there are your eigenvalues. Right, now, you get different eigenvectors for each eigenvalue. So that's what we've got to watch and make sure we do now. Right, so these are your eigenvectors. And our first one is going to be when lambda equals -1, because that's my first eigenvalue. Right, so our eigenvalue equation, or our eigenvector equation, is A take away lambda I x equals 0. That's your eigenvector equation. Oops. Seems like I copied this. Right. So A, our original matrix, so that's 2 take away lambda, 7, -1 and -6 take away lambda. And now, because this is a 2 by 2 matrix, this vector x is x1, x2. If it was a 3 by 3 matrix, it would be x1, x2, x3. And what we're saying is that is equal to 0. Okay, now what we do is we substitute in this eigenvalue that we worked out up here. So it was 1 rather than -1. Right, so we're going to substitute this into here. So 2 take away 1, 1, 7, -1, -6 take away 1, -7, x1, x2 is equal to 0. Right, now what we want to do is, let me just get rid of this nonsense. Just the way it's copy and pasted over. Right, what I want to do is make this upper triangular. And remember, upper triangular means you want to, if it's a 2 by 2 matrix, you want to have 2 numbers there and a 0 there. Right, so there needs to be a 0 in that corner if it's a 2 by 2. And if it's a 3 by 3 matrix, you need to have zeros in the bottom 3 corners and then other numbers there. Now, the other numbers can be 0, right? That's not a problem. But the key thing is that has to be 0 in a 2 by 2 matrix, or if it's a 3 by 3 matrix we're dealing with, it has to be those 3 there. And remember, we do that using row manipulation, right? So this is a matrix here I'm looking at, 1, 7, -1, -7. So I keep the top row the same because that's fine. I don't need to do anything to that. Now you can sit and do the matrix manipulation or the Gaussian elimination type stuff somewhere else if you want, or you can just do it as I'm doing it inside the problem. Right, so I need to make this 0. So if I just do R2 plus R1, okay, so R2 plus R1 here, well that would give me 0. R2 plus R1 here would give me 0. Okay? And that means it's now upper triangular because we've got a 0 down here. And that's all I needed to do. So that means I'm left with 2 equations, right? The bottom equation is 0x1 plus 0x2 is equal to 0. 0x1 plus 0x2 is equal to 0. That doesn't tell me anything, so I can just ignore that. But sometimes it will. Sometimes it will be useful, but a lot of times you will just get 0, 0 down here. But I just want to give you a kind of general case for everything, so it doesn't cause you any grief. Right. Okay, so in that top row though, I'm giving it 1x1 plus 7x2 is equal to 0. So I just do that thing that I did a minute ago. So I move the x2's over to the other side. So x1 equals -7x2. So that means that my eigenvector is x1 is equal to -7 and x2 is equal to 1. And just to prove it, and what makes something an eigenvector is just putting this little t outside of it to show you it's a general case for all eigenvectors. So that you can be multiplying that by 2, multiplying it by 4, multiplying by 6. The eigenvector stays the same. So that's my eigenvector when lambda equals 1. So you set up the equation. It's the same matrix as we had before. And we take away whatever our eigenvector is from the diagonal, and we're left with a matrix. We do our row manipulation. In this case, it was R1 plus R2. And then we get two equations. And luckily, first equation didn't tell me anything, but the second equation told me everything I needed. So that's the eigenvector for lambda equals 1. Now, I'm not finished yet because that's only one of the eigenvectors. So I've now got the exact same thing. So I've got 2 take away lambda, 7, negative 6, sorry, negative 1. Oops. And negative 6 take away lambda. x1 is 2 is equal to 0. So that's what I had before. That's what I did for the first eigenvector one, but my eigenvalue is different this time. So that's 2 take away negative 5, 7, negative 1, negative 6 take away negative 5. x1 is 2 is equal to 0. So now I need to simplify that. You could have just done that in one step. You didn't need that middle row in there. That's just me trying to show every possible step in case anyone doesn't understand something. There we go. Now, the top row is fine. Now, obviously, as this becomes 3 by 3, it becomes a bit more difficult. And it's only this matrix that we're changing the rows, and it's nothing to do with anything else that's here. Right, so if I do 7 R2 plus R1, because 7 of these plus 1 of these would give me 0, because it needs to be 0 in here. So that would give me 0. 7 of these would also give me 0. So I've got the 0 in the bottom corner. And as I said, what happens a lot is you get both those bottom values being 0. Right, so that bottom equation isn't going to help me. So I'm just going to have 0x1 plus 0x2 equals 0 again, but the top equation will. So 7x1 plus 7x2 equals 0. So 7x1 equals negative 7x2. Now remember what I said in that note 4 when we're going through the method. If you can simplify these by taking a common factor or whatever, then you can, then do it. These have both got a common factor of 7. So that would be x1 equals negative x2. So that means your eigenvector we'll split this t. x2 is going to be, sorry, x1 is going to be negative 1 and x2 is equal to 1. It's just the corresponding coefficients of the other part of your equation. And that is the eigenvector for lambda equals negative 5. So that's my 2 eigenvalues and my 2 eigenvectors. So the next thing is a 3 by 3 question or example. However, I think there's been a lot done over the course of this week and last week in terms of stuff you've handed in to me and all that kind of stuff. So I'm not going to proceed much further. What I want you to do in the Eigenvalues and Eigenvectors book, if you can go to page number 13 and try questions, well, there you go. 1 is using a previous example, 2 and 3. But if you focus on 2 and 3, that's cool. So I gave you the 3 questions on eigenvalues during the lecture, and now I want you to try those 3 questions from page number 13. Next week, I'll try and finish off eigenvalues and eigenvectors if I can. Then we've only got double integration to do, which will maybe be the week after that. Some time for revision, and then I'll give you a couple of weeks to do the assignment again. Kieran asked me what the pass mark for the assignment is. I don't know. I've not made the question paper up yet. That's something that I need to try and do. Okay, so hope everyone's well.